Hello friends, welcome to the course Essential of Data Science with R Software 1, in which we are trying to understand the basic concepts of probability theory and statistical inference. So you can recall that in the last lecture we had initiated a discussion on the confidence interval estimation, and I had simply given you the basic concepts, basic definitions, fundamentals. And now in this lecture we are going to take one example. The example is that we are going to consider a sample from a normal population, and we will try to obtain the confidence interval for the parameter mu. Now, for sigma square you have two options, whether sigma square is known or sigma square is unknown. So, in this lecture we are going to consider sigma square to be known, and in the next lecture I will try to consider the sigma square to be unknown. So, now in this lecture whatever we had learned in the last lecture, that we are going to implement it, right. So, what you have to do, that you simply have to follow the methodology, that how are we going to obtain the confidence interval, what are the steps involved. Once you understand these steps, then after that finding out the confidence interval for most of the probability distributions or any parameter of those probability distribution will not be difficult. That will be pretty straightforward. So, my request to you in this lecture is that please try to follow the steps. Okay, so let us begin our lecture. Right. So, now we are considering the situation that we have got a random sample from a normal population. Sample is x1, x2, xn, and in this normal population the mean here is mu, which is unknown, and sigma 0 square is the variance, which is known. Now, you have learned how are you going to estimate the parameter mu through the point estimation, and we had obtained that the point estimate of mu was x bar, either under the case of method of movements or the maximum likelihood estimation, right. And now we want to construct the confidence interval around the mean mu, right. So, what we try to do here, now you have to first understand that you need to somehow find the vital quantity first. Once you can obtain this thing, your job is nearly done. After that there is only simple algebra that you have to follow in a very systematic way. So, the main concern lies that somehow under the given circumstances you have to find a vital quantity which is depending on the values of x1, x2, xn and the parameters of the distribution, but its probability distribution is independent of any of the parameter. So, now you can recall the center limit theorem. We had proved there that x bar follows a normal distribution with the same parameter mu, same mean mu, and variance sigma square upon n. So, now here the variance is sigma 0 square. So, the variance becomes here sigma 0 square upon n, which is a known quantity. And we also had learned that square root of n x bar minus mu upon sigma 0, this follows a normal 0 1. So, this is essentially x bar minus mu upon the standard deviation of x bar, which is sigma 0 divided by square root of n. So, we know that this is going to follow a normal 0 1, and you can now see that this is your vital quantity. This itself depends on x1, x2, xn and mu, but its distribution is depending on normal 0 1, which does not involve any unknown parameter mu, right. So, now we have to just construct the confidence interval, and now you just try to observe that how simple and easy it is. So, we know what we need to find. Now, using this NPTEL quantity whose distribution is normal 0 1, it will be like this one. So, we need to find that this quantity is square root of n x bar minus mu divided by sigma 0 should lie between minus z alpha by 2 and plus z alpha by 2, like this, minus z alpha by 2 and z alpha by 2. All the symbols and notation now they are known to you. And the probability of such an event is exactly equal to 1 minus alpha. You see, when you are trying to use the continuous distribution in which you are trying to find out the confidence interval, we can very easily assume the equality sign. But in case if you are trying to consider it for the discrete random variable, then you have to be careful, right. At any rate, let us try to concentrate on this issue. Now, you can see here that you simply have to solve this equation. So, if you try to solve this equation here, this will become here minus z alpha by 2 into sigma 0 upon here square root of n, which is lying between x bar minus mu, and this will be plus z alpha by 2 into sigma 0 upon root n. And you want to know what is the range for mu. So, now you have to simply solve this thing. This x bar will go on the left hand and right hand side, and this will become that mu lies between x bar minus z alpha by 2 sigma 0 divided by square root of n and x bar plus z alpha by 2 sigma 0 divided by square root of n, right. And you know that this z alpha by 2 is the 100 alpha by 2 percent point on the normal 0 1 distribution, or they are the alpha by 2th quantile of normal 0 1. So, now I can say here that this is the value of lower and upper limits of mu, right. So, this is the lower bound and this is the upper bound, right. So, I can say now here the 100 1 minus alpha percent confidence interval for mu is like this, that theta hat L x in your earlier notation is given by like this, x bar minus z alpha by 2 sigma 0 divided by root n, and theta hat u x, this will become x bar plus z alpha by 2 sigma 0 divided by root n. So, now you have obtained, and you can see that these two limits they are depending on the value of capital X bar, and that is what we said that this is statistic. These are two statistics, theta hat u and theta hat L, because they are going to be random, right. And in case if you try to prove that whether this interval is good or bad, then we can prove statistically also that the length of the interval is the shortest. So, the length of this interval is found as x bar plus z alpha by 2 sigma 0 upon root n minus x bar minus z alpha by 2 sigma 0 upon root n. So, this x bar gets cancelled out, and the length of the interval here is simply here 2 z alpha by 2 sigma 0 upon root n. So, this is the length of confidence interval. Briefly we write many times CI, confidence interval, right. So, this interval that you have obtained here, this is the shortest confidence interval. So, for example, if you try to take here alpha is equal to 0.5, then this interval will be called as 95% confidence interval for mu. And in case if you try to see the value of z alpha by 2 for alpha is equal to 0.05, this will come out to be 1.96 from the table. I will try to show you that we can obtain the same value from the R software also, that you actually have now learned, because this is simply your here quantile, right. And the value of x bar can be obtained from the sample, small n is the value of the sample size, sigma 0 is known. So, now for a given sample x1, x2, xn, you can find out the value of lower and upper limits of the confidence interval. And you can see here, this is a two-sided confidence interval, right. And in case if you try to plot it also, this will look like this, that there are two limits and somewhere it is in the, there is the parameter, right. For example, like this you can see here, right, that in case if you try to see the curve for the distribution of your pivotal quantity, let me try to show you here this quantity, right. So, this is the distribution of square root of n x bar minus mu upon sigma 0. So, you can see here it will look like this, that the mean here is 0 and here this is minus z alpha by 2 and here on the right hand side this is plus z alpha by 2 and this area which is here shaded in green color, this is actually alpha by 2. So, obviously, this area which is here in the dotted, this is 1 minus alpha, right. And when you are trying to find out the confidence interval, then it will look like this, that mu here is here and on the left hand side of the mu we have here the value of theta hat L and on the right hand side of the mu we have theta hat u, right, which are given by x bar plus minus z alpha by 2 sigma 0 upon root n. And you can see here this shaded area here and here, this is alpha by 2 and this area here in the middle, this is 1 minus alpha, right. So, this is what we mean, that this is the area which is the confidence band, right. Now, in case if you try to see, if you want to compute this interval in the R software, well, there is no direct command in this case, but when we are trying to do the case when sigma square is unknown to us, then we have a direct command and we can obtain the confidence interval directly. So, if you try to see the structure of this interval, the lower limit and the upper limit, then means you know how to compute each of the factor, each of the term. For example, this can be obtained by say here mean, and this z alpha by 2 can be obtained by here q norm that you have used when you did the normal distribution. And this here n is here the number of observation. So, this can be obtained as the length of the data vector and sigma 0 is known. So, we can very easily write a one line command for obtaining the lower limit, and similarly, because by changing the minus sign to plus sign, we can write a one line command for the upper limit also, right. So, for example, if I say that alpha is equal to 0.05, so you want here 95% confidence interval. So, this area here is alpha by 2, this area here is alpha by 2. So, alpha by 2 is going to be here 0.05, right. So, this area here is going to be 0.025 quantile. So, this can be obtained by here q norm 0.025 and this point here, this area here is 0.025. So, this point is actually here this side, this is the point here which is 97.5% of the area. So, this is here 97.5th quantile, right. So, you can obtain any of this value and then you have to use it appropriately, right. So, now I can write down the lower limit of the confidence interval as a mean of x. Suppose x is the data vector, then q norm 0.975 into sigma 0, which is given to us some known value, and square root of length of x data vector. And similarly, if you try to change this sign from minus to plus, you can obtain here the upper limit of the confidence interval. And I will try to show you all these things as an example also. So, you can see here this is essentially a two-sided confidence interval, right. And similarly, you can also find one-sided confidence interval. For one-sided, what will happen? Like this, there are two options, that your this alpha is on the right hand side or on the right tail of the distribution, or alpha is on the left hand side or the left tail of the distribution, right, and the remaining area will be 1 minus alpha in both the cases, right. So, in say case number 1, this point is going to be here z alpha, and in the case number here 2, this is going to be minus z of alpha. So, now we can define the one-sided upper confidence interval, which is obtained by this quantity, vital quantity, square root of n x bar minus mu divided by sigma 0 is less than equal to z alpha, right, is equal to 1 minus alpha. That means probability that this area is equal to 1 minus alpha. And if you try to solve it, you can just put this sigma 0 on right hand side, bring square root of n over here, simply solve it, and then you will get here that probability that x bar minus z alpha sigma 0 upon square root of n is less than equal to mu, and this is equal to 1 minus alpha. So, I can say that 101 minus alpha % one sided upper confidence interval for mu is like this: x bar minus z alpha sigma 0 divided by root n to infinity, right, as simple as that. And similarly, if you want to find out the one sided lower confidence interval for mu, this can be obtained by solving that square root of n x bar minus mu divided by sigma 0 is greater than or equal to z alpha, and the probability of such an event is 1 minus alpha, and if you simply solve it, this will solve that mu is greater than or equal to x bar plus z alpha sigma 0 divided by square root of n, and the probability of such an event is 1 minus alpha. So, I can say that the 101 minus alpha % one sided lower confidence interval for mu is minus infinity to x bar plus z alpha sigma 0 divided by square root of n, right. So, now you have obtained all these things, and I will just try to show you here that this concept of confidence interval also helps in finding out the value of sample sizes, and it helps us in choosing the sample size. So, how? That is a very popular utility of this confidence interval. So, here if you try to see, we are essentially using this x bar to estimate the unknown parameter mu. So, the error what is happening that some values are lower than mu and some values will be upper than mu. So, I can write down this deviation or this error as capital V, which is the absolute value of the deviation between x bar and mu. So, we can make a condition, we can impose a condition that this error is less than or equal to z alpha by 2 sigma 0 divided by root n with confidence 101 minus alpha, right. So, in this type of situation where the sample size can be controlled, so that we can choose the sample size is small, and so that we are 101 minus alpha % confident that the error in estimating the parameter mu is less than a specified bound on the error e, that you are sure that you are not making the error more than this. So, in this case what we can do, this z alpha by 2 sigma 0 divided by square root of n can be substituted as capital E, and this can be solved, and we get here the value of small n to be z alpha by 2 sigma 0 divided by E whole square, and this is the appropriate sample size, right. So, now let me try to take an example and try to show you all these things. Okay, so suppose a sample of size 20 on the day temperature in a particular city is collected. So, temperature of this 20 days in a city that is collected, and we assume that this temperature is following a normal distribution mu sigma square, and suppose sigma square is known to. Now, the sample values of the temperature are obtained here like this in degrees Celsius. Now, if we know that if you want to find out the estimate of mu as a point estimate, then we can compute the sample mean, and if you try to compute the sample mean of all this value, this will come out to be 41.97 degree Celsius, right. But now we are interested in finding out the interval estimate of mu. So, we try to use the earlier obtained expression, and we try to obtain the 95% confidence interval for mu whose lower and upper limits are obtained as like this theta hat L and theta hat U based on x1, x2, xn, which are obtained by these two limits. So, now we can obtain the value of sample mean, it is here 41.97, the value of Z alpha by 2 from the table can be obtained as 1.96, or that can be obtained directly from the R software also, and then sigma 0 is square root of 36 and small n is 20. And similarly, you can write down here the upper limit also, and you can solve it, and this will come out to be approximately 39.34 to 44.59. That means the mu is expected to lie in the range 39 degrees to so almost 44 degrees, right. And you can see here that this sample mean x bar, which was the point estimate, this is lying inside this interval, and it is lying in the mid, means if you try to take this value somewhere in the mid, this will be your here the value of mu hat is equal to x bar, right. So, now we can say with 95% confidence the true parameter mu is covered by the interval 39.34 to 44.59. This is the interval estimate, and whereas this is the point estimate that you have to just keep in mind. So, you can see it is not difficult to obtain them. And in case if you want to determine the value of n, that is the sample size such that we are 95% confident that error x bar minus mu, that is the absolute value of error will not exceed is say 0.5, then I can use this expression of n, and I can simply substitute here the value of Z alpha by 2 as 1.96, sigma 0 as 6, and error here as say 0.5, and we can obtain here that the approximate sample size is going to be 553, right. Okay. So, that means you need the 553 number of observations. Okay. So, now let me try to do the same thing in the R console also. So, I have just entered this data in the data vector say here temp, and then I am simply trying to compute the theta hat L and theta hat U by these two expressions, and you can see here that these value come out to be like that, means sigma 0 is given. So, I have to enter it separately, and then the lower limit will come out to be here like this, mean temperature minus q norm 0.975 and sigma 0 is square root of length and temperature. This value will come out to be 39.33, and similarly you can obtain the upper limit just by changing the minus sign to plus sign, and you can obtain here these two limit 39.33 through 44.59. So, now I have entered the data on here temperature as temp data vector. You can see here I need to give here the value of sigma 0 here as say 6, you can see here like this, and if I try to compute here the lower confidence interval, this will come out to be like this, the same expression that you have just used, and if I try to just change this minus sign to plus sign, this will be upper confidence limit, right. And surely if you try to change here your this alpha, that means suppose if I take here only the 75th quantile, you will see here this value is going to decrease, right. So, it depends on the value of alpha that how are you going to obtain the confidence interval. For example, if you try to take here the 75th quantile, then it is going to be the interval is going to be shorter. The length is now between 41 to 42, whereas in the earlier case the length here is 39 to 44, right. Okay. So, now let me come to an end to this lecture. I have given you the details that how are you going to construct the confidence interval in a normal distribution for the mean when the variance is known to us. Now, in practice this variance may not be known to us. In that situation, what we are going to do? We will simply try to estimate it, replace it there, but the question comes, how are you going to find out the pivotal value? So, that I will try to show you in the next lecture, but it is important for you in this lecture that you try to do the same algebra with your own hand manually, and try to understand how can you obtain the confidence interval. This methodology, you will see that it is applicable in most of the cases whenever you want to find out the confidence intervals for different parameters in different probability functions. Right. So, you try to practice it, and I will see you in the next lecture. Till then, goodbye.